Great. Thanks, Lorenzo. Hi, everybody. I'm Ed. So I'm director of the Robot Learning Lab at Imperial. And really the work that we focus on there is on robot learning. So that's the intersection of machine learning and robotics. So the way I often think of this is in classical robotics, you would sort of manually design, either you would manually design a controller, or you would manually design some dynamics model and some cost function and some way to optimize a controller using that dynamics model. In robot learning, you don't manually design the controller or the sort of the reward model and the optimization of the controller directly. You design an algorithm which can learn from data, and then you also design a method through which a robot can obtain that data. And so the idea here is that even though for many tasks you could manually design a solution for them, often it's the case that it's actually quicker and easier to have a general robot learning algorithm that you can apply to lots and lots of different tasks, rather than having to go and create solutions manually for each individual task. So there's still something you have to design as an engineer. It's not all just sort of magic. You design the learning algorithm. But then you can apply that same learning algorithm to lots and lots of different tasks, and the only difference between each task is that you give it different data. And then it's much easier to scale to other tasks because collecting data is relatively easy, whereas manually designing a controller for every task is actually very, very difficult. So there's still kind of science and engineering in robot learning as there is in more classical engineering and robotics. It's just that you're shifting the engineering to designing a learning algorithm rather than designing the controller itself. And my particular area is imitation learning, which is enabling robots to learn from demonstrations. So in imitation learning, the data that you provide the robot is data from demonstrations of tasks. So that could be a human performing the task, or it could be a human teleoperating a robot. But that's relatively easy to collect because you just do the task, right? You don't have to think about the underlying controller. You just do the task and the robot will learn from that data. And within that field, the area that I'm really interested in is called one-shot imitation learning, which is how a robot can learn really, really quickly. So as a human, if I were to show you some task like, I don't know, pick up this thing of sugar and like, I don't know, put it there or put it in that, you could probably come along and all do that very easily, right? You wouldn't need to sort of have thousands of demonstrations to learn that. And you wouldn't need to try it and with reinforcement learning and try it and get feedback until you've done it. So humans are very good at learning from one demonstration. And so I think, well, there's probably a way to get robots to learn from one demonstration as well. Like if a human can do something, a robot should be able to do it. There must be some method out there to get robots to learn quickly like humans. So that's what we've been working on for the last 3 years. But it's not the way that most people do imitation learning. And certainly all of the big companies and all the big startups that you'd have heard about, like Figure, will not be doing one-shot imitation learning. They will be doing something which is called behavioral cloning. So these videos that you'll see of humanoid robots performing tasks look very, very impressive. And these are robots running AI systems, so neural networks that map images to actions. So it's very impressive in that sense, but what you don't see from this video is that it probably took weeks or months of data collection and training for that robot to learn that task. And in many cases, if a robot takes weeks to learn a task, it's too slow for that robot to be useful, because it may be that you only want the robot to do that task for like a few days. So particularly in manufacturing, if it takes a robot a month to learn a task, you might as well spend a month designing a solution for, like a traditional robotic solution for that task, like a traditional systems integrator. So really all we've done here is we've shifted the problem from a systems integration problem of more traditional engineering over to a data collection problem, but it would still take weeks or months to collect that data. So often it's not very practical to use these methods in industry. So what I'm interested in is getting this kind of behavior, but by showing a robot once. So you can imagine this task here, robot performing that task. you could just do that task once yourself, and a robot would then be able to perform that themselves. And this is how you would teach a human in a factory, right? You would show that you would say, right, today I want you to put this on there and then screw that in and then do that. And you would step away, and that human would then go and do that job for that day. So if we really want robots to be a genuine alternative to human labor, they probably need to work and learn as quickly as humans. So I'm just going to teach you a little bit about what this traditional approach to imitation learning is, which is the approach that you would have seen in that video. It's called behavioral cloning. So imagine we have a robot gripper here, and the task is to open the lid of a box. What we're going to do is we're going to collect some demonstrations. So each of these is a state that the gripper is in, and we're going to move the gripper through these lines and collect data to show the robot how to perform the task. And then we're going to train a neural network on this data, and we're going to then do some inference. And at inference, you're going to put the robot in a different state, somewhere along this green line, and expect the robot to perform the task, even though it's never actually seen this state, okay? It's only seen the blue states, it's never seen the green states. And so the controller, the policy, needs to generalize from the blue states to the green state. And if this function is nice and smooth, then you can imagine there's going to be some kind of nice generalization here. But you do have to collect lots and lots of data, okay? Otherwise, the generalization isn't going to be very good. And typically with behavioral cloning, this is how demonstrations are collected. There will be some mechanism to teleoperate a robot. There are other ways to collect the data as well, but this is a very common way of doing it. So you can see here, somebody at the top is actually moving a sort of teacher-student setup where or leader-follower setup where the leader arms at the top there are being moved by the human, and the robot is then following those arms. This is a way to collect data. And then you can train a neural network on this data. And so that neural network would be a network that takes in the image that the robot sees and then maps it to the action. It's very simple. It's just supervised learning on image-action pairs. And if you collect enough data and cover the state space sufficiently densely, then that neural network should be able to generalize to these unseen states. And here's an example of a policy that is learned with behavioral cloning. And this robot can tie shoelaces together. So this is like really, really impressive, really precise and quite dexterous behavior. But it would require, I think, on the order of tens of thousands of demonstrations to teach this robot this one task. So it's really nice behavior, but imagine how long it takes to collect 10,000 demonstrations. It will probably be weeks, if not months, of data collection. I mean, as soon as you change the shoe with different shoelaces, you probably need another 10,000 or so. So it does work at scale. But like a lot of things in engineering, if you have time to come up with a solution for something, you can probably, for example, you could probably manually design a machine for that one shoelace that puts the shoe in exactly some known pose and initializes the shoelace in some perfect known pose, and then it does a sort of blind movement in order to tie the shoelace. And if you spent a month thinking about that problem, you might be able to get a solution. So spending a month collecting demonstrations doesn't really solve that problem. It just transfers it from from a controller engineering problem to a data collection problem. But anyway, the point of this does work. Machine learning in robotics does work, and these policies are really, really impressive, but they're really slow for robots to learn from them. So let's look at this again. The blue dots are the data that you would have collected from the teleoperation, and the green dots show the states that the robot is now going to see during testing, and what we hope is that these green dots are sufficiently close to the nearest blue dot that this function is going to generalize well, and the action that's predicted for the green dot is good enough to solve the task. And with sufficient data, you will have that density of data that will give you nice generalization during inference. But with one-shot learning, we have to think about it differently. So imagine this is a demonstration, and now at inference, you're going to initialize the robot here. This time, the image that the robot captures here is going to look very different to any of these images here. And you're probably not going to be able to generalize this policy to this observation here. It's too far away. And so if you did behavioral cloning on this kind of demonstration, it would fail completely. Anywhere that isn't exactly here. And even if you did initialize the robot here, it would sort of start going in the right direction, then there would sort of end up like here, and then suddenly it's well out of distribution, and it would just be predicting random motions, and then it would just sort of, go here. So behavioral cloning doesn't work with a single demonstration, and we have to think more carefully about the problem. And we've basically got to figure out, okay, well, how can we go? Well, one way of thinking about it is how can we go from there to there? But there are other ways to kind of conceptualize the problem. All right. So the rest of the talk, I'm basically going to take you through a few different ideas that we played around with at Imperial to solve this problem. And all of these methods are based on a single demonstration per task. And none of them are using behavioral cloning. So one project that I worked on myself many years ago is based on self-supervised robot learning. So this is me in my lab. And I'm going to teach a robot how to hammer in a nail. And this robot has a camera here, which is recording what this scene looks like from the robot. So I'm collecting a demonstration here, single demonstration of hammering in the nail. And then what happens is I step back, and the robot is going to collect a data set of image and action pairs. And these are the images it sees. And then it's basically collecting for each image what action would take the robot back to this point here. We call this point the bottleneck, so it's kind of the point where all the trajectories converge. And then we collect a second data set, which is even closer to the object, just this kind of fine-grained data set around the object. And again, we collect pairs of images and actions to show the robot what action it should execute for every image. And then what we can do is, you can think of this a little bit like collecting this data, but automatically. I don't have to move the robot physically here. It can just kind of move around like this automatically and automatically label the action here, because it just knows how to go from here to here. Because this is just doing calculations in 3D space, how to go from there to there. So it can automatically collect that data, and it can label that data. And then what we can do is we can train a policy that will move the robot from any state to that bottleneck pose. And this is what it looks like during testing. So the robot is executing a policy. It's taking images, passing through the neural network, and then executing the action. And then it's going to use that second data set, which the fine-grained data set, which is trained on a second neural network, to make one final correction. And then finally, we're just going to replay the demonstration. So it's a really simple idea of alignment and replay. We align the robot with the object in the same way that it was aligned during the demonstration, and then we simply replay the demonstration. And then you can get all these nice behaviors like this. So each of these tasks was trained on just a single demonstration, and then about 20 minutes of data collection and 20 minutes of policy learning. And you can get really nice behaviors like here, like scooping up a bag, hammering in the nail, lifting lids, insertion tasks, like fine-grained insertion tasks here, screwing with a screwdriver. All of these things that, if you did this with behavioral cloning or reinforcement learning, would actually be really, really difficult for various other reasons. But by framing it in this way, with this alignment and replay, we can get this really, really nice behavior with these dynamic kinds of behaviors like the scooping task, where the velocity is really important, and just replaying the demonstration actually gives you that capability of incorporating that sort of dynamic behavior. And so we can get these really nice policies that work across a range of different tasks, and all of these were learnt with just a single demonstration each. Okay, so after this project, I thought, right, that's really nice, and we were able to get robots to learn these tasks with a single demonstration followed by 40 minutes. So 20 minutes of data collection that's autonomous, and then 20 minutes of training a neural network. I then started thinking, well, actually, what I'd really like is a robot that doesn't need that 40 minutes at all, where you can provide a demonstration, step back, and then the robot will just perform the task instantly. And so a lot of our work since this project has been on this idea of instant robot learning. One demonstration, no training at all, just the robot performing the task straight away. And the first idea we had for this was based on pose estimation, so object pose estimation. My background, my PhD was in computer vision, so I always thought about how we can bring in computer vision ideas into robot learning to give us data efficiency. So let's imagine we've got a robot and we're teaching it how to scoop up an egg here. And this is the demonstration on the left. We're scooping the egg. And then on the right-hand side, we've got the live scene, which is what the robot sees during testing. And what we want to do is to execute that same trajectory, but the pan and the egg are now in a completely different pose to where they were during the demonstration. And what you can do is you can imagine if you know the pose of this object or the pose of this object relative to this object, you could simply transform the trajectory by that same amount and then execute that trajectory for this new pose. But the problem is, traditionally with object pose estimation, you assume there's some kind of object model because if you were to do pose estimation of this, you would assume there's some object model, like a 3D model, and you would predict what is the pose of this relative to this 3D model. But we don't want to do that. We don't want to assume that there are models of every object in the world, because then you can't just go and grab a random object and teach a robot on that random object. And so we decided not to go for kind of classical pose estimation, but to go with what we call unseen object pose estimation, which is where this is the first time the robot has ever seen this object. So you can imagine the robot sees this object during the demonstration, and now this is the live scene. We've got to predict a 3D transformation that in the camera frame tells us what is the pose of this relative to the pose of this. And to do that, we train this in simulation. So we trained with lots and lots of pairs of random objects. Each one, there's a 3D transformation between them, and we can render images in simulation. And then we also know the ground truth transformation between the two. So we can have a data set of image pairs and the transformation as the label, and then train a neural network to predict that transformation label from the image pairs. And then what we can do is we can put, because this will generalize across other objects, we can put in a random pair of objects, and it will predict the transformation between the two, and then we can transform the trajectory by that same amount. And then this is what this looks like when we test it out. So we are scooping up the egg with a single demonstration, and then we're stepping back, and this is one uncut video, and the robot is executing that unseen object pose estimation method in order to figure out where the object is relative to that demonstration. And we're getting invariants and distractors here just by segmenting out the object of interest. And this works for a range of other tasks as well. So all of these tasks we're using unseen object pose estimation, but none of these objects were in that training set. The training set for the object pose estimation was just random objects in all sorts of different poses. And so again, we're getting this really nice behavior where we can teach a robot a new I wouldn't call this dexterous necessarily, but this is a manipulation task, and we can do it with a single demonstration, but then no waiting around. We just provide the demonstration, step back, and the robot is just able to perform that task instantly. Okay, we then, over the last year or so, we worked on a project where we really scaled this up, and we decided to see how quickly we could learn 1,000 tasks. So if you can teach one task with one demonstration, how quickly would it take you to collect 1,000 demonstrations, which would be the required number to teach 1,000 tasks? And we managed to do that with less than a day, okay? And so we thought, well, let's call the project Learning 1,000 Tasks in a Day. And this project, this actually ended up in the front cover of Science Robotics. And the challenge was, we've got 402 different real-world objects, and we've got a bunch of different verbs or skills. So a skill is a verb, so zip, swipe, dust, for example. but there are 1,000 different tasks. So one task is an instance of object. So each time there's a new object, that's a new task. And we collected this data, 17 hours of data collection, one demonstration per task. And we actually recorded the entire data collection process. So these are my students, Cameron and Pietro, in my lab at Imperial. And we thought, well, wouldn't it be fun just to record the entire process of collecting 1,000 demonstrations? So we did that. We put the camera in the corner of the lab, and we just let it run for this entire data collection process. Their clothes change over the period of this video, so they're not actually here for a period of 24 hours in one go, but the accumulation of chunks of time was less than 24 hours. And then what we did is we did a lot of experiments on generalization. So given 1,000 tasks, can we then generalize to the 1,001st task? And how was the performance on those 1,000 tasks that it had been shown? And we did lots of comparisons between this and the traditional behavioral cloning methods. But ultimately, what we found was that we really can scale this up, and we can get robots to learn a very wide range of tasks. So these are kind of everyday household type tasks. Each of these learned with just a single demonstration. And so we basically, so far in the talk, we've gone from something that takes 40 minutes to learn a task to something that requires 0 minutes to learn a task. And then we've scaled it up to 1,000 different tasks and seeing the fact that this really does work across a really very large number of different tasks. Oh, and here's just some more videos showing even more diversity here. Okay, so for the second part of the talk, I'm going to talk about something called in-context imitation learning, which is something we've also been working on lately. In-context learning is something that emerges in large language models. So if you were to take a large language model and give it examples of inputs and outputs, so lots of inputs and outputs, so maybe question, answer, question, answer, question, answer, question, answer, the language model, without having to update its weights, would be able to learn the problem that you're trying to teach it. And we wanted to see whether we could do the same thing in robotics. So rather than having to train a policy where we actually update the weights of the neural network on robotics data, we wanted to see whether we could use a frozen, pre-trained neural network to very quickly learn a new task without having to actually update the weights of the network. So let's see what in-context learning looks like with LLMs. If you were to put this pattern into a large language model, it would be able to complete this pattern for you. Nowadays, you could just take an image of this slide and it would just complete it for you. But certainly, if you put this sequence of data in, it will complete the pattern for you. And what this pattern is these are different vertices of different squares. So that top row is this square here. And really what I'm asking it to do is find out what that vertex is of this square. So there is some structure in this data, and it's these corners of these vertices of these squares. And a large language model would be able to figure that out, because this is an example of a piece of data. This is another example. This is another example. It's doing pattern recognition, but it's not being trained. The weights of the neural network are not being trained with this data. You're simply prompting it with this data. So this is why it's called in-context learning, because you prompt it with examples of data, and the pre-trained neural network is able to then learn that task instantly without you having to actually update the weights of the neural network. So we wanted to see whether we can do the same thing in robotics. Now the problem is in robotics, the equivalent in robotics would be, instead of putting in vertices of squares, we put in demonstrations. Okay, so we want to prompt a large language model with some demonstrations of data. And then what we want to do is say, right, now at test time, given this prompt plus the test observation, what is the optimal action for the robot to execute? The problem with this is, like, robots don't reason in language in terms of interacting with objects. They reason in images and 3D space, which is not the same space as text and language. So we've got to figure out a way, if we're going to use a large language model to do in-context learning, we've got to figure out a way to interface that language model with image and 3D data. And so what we tried out was we looked into extracting key points from the images using dyno features. So dyno features are these nice semantic features which, for every patch in an image, will give you some feature. And given two images of the same object, you can kind of find correspondences between the two images based on these dyno features and extract key points. So in these images, we've got the same object in different poses, and you can see here these key points represent semantically the same parts of that object. So now we have a way to represent this object with positions of key points. So by defining the 2D positions of these 4 key points, that actually defines the 3D pose of that object. And now what we can do is we can turn this whole thing into a prediction of numbers, and specifically a prediction of the points, the coordinates of these key points. So let's look at what this looks like during training a task. We're going to provide a demonstration of a task. Well, first of all, we're going to extract these key points. Oh, sorry, I think I skipped ahead there. Yeah, okay. Let's go back to this. So, okay. First of all, we're going to take this object, put it in front of robot, and extract key points. So the pose of the object is now represented by the positions of these key points. And then what we're going to do is take the 3D positions of these key points, and these now become part of the prompt that we're putting into the neural network, into the language model. And then we're going to move the robot to perform the task, so grasping this bottle. And we're also going to represent the positions of the robot by the positions of its key points. Okay, so each key point here, again, is represented by 3 numbers, just in the way that the key points on the object are represented by 3 numbers. And then the entire demonstration is a sequence of inputs representing the pose of the object, and also outputs representing the actions that the robot should execute. And now you can imagine one demonstration is a list of key points which together shows where the object is and what the actions should be. And then another demonstration would be similarly another list of key points for both the object and the actions. And then we can do this in context learning. So rather than just putting in coordinates of points in the squares, we're going to put in coordinates of these key points. And then we're going to put in, so imagine these 3 are the coordinates of the object key points, then this one is the coordinate of the robot key points. So this is basically the action that we want to predict. We could do 1 demonstration, 2 demonstration, 3 demonstration, and then the 4th one is like the sequence of observations or the positions of the object, and then we ask it to predict what the action should be for the robot to execute. And then at test time, this is what this looks like. So we're taking in the 3D positions of each of these key points. This is the demonstrations, and now we're adding the key points for where the object is, and it's predicting the key points for the robot, which is basically the actions of the robot. So it's imagining where these key points should be in 3D, and then the robot is just going to move through that sequence of actions. So we're using the large language model to basically do extrapolation and interpolation and multimodal learning using a fixed pre-trained neural network without having to actually then fine-tune the weights of the neural network on robotics data. And we can do this across a range of different tasks. So each of these tasks was trained with 5 to 10 demonstrations, with demonstrations covering different spatial positions of the object. And then we're simply prompting a large language model with those demonstrations and the current observation of the live scene, and then it's able to predict the actions that robots should execute. And this is a really interesting graph because, so what we're seeing here is a few different methods. So we're showing as the number of demonstrations increases, how does the performance increase? So this is the success rate. So the method I just showed you is this, this blue one. And what we're seeing here is that it's very good when there aren't very many demonstrations, but then once you have lots and lots of demonstrations, you don't really get a huge amount of benefit with more demonstrations. And that's because it's hard for a large language model to reason about a long context. Okay, this long context is very difficult to extract all the intricacies in that, the pattern. The green one is diffusion policy, which is basically a behavioral cloning approach. So this is a kind of an approach that would just take in images and map them to actions. And this is the performance given this number of demonstrations. So you can see it doesn't work very well, but at least it is scaling quite nicely. So with more demonstrations, these behavioral cloning approaches do get better and better and better. The orange graph is a method where we took the key point representation. So rather than just using images of the observations, we use the key points of the objects. So it's a much lower dimensional representation of the observation. And then we did diffusion policy on that. So diffusion policy to behavioral cloning. And so you can think of this as kind of the best of both worlds in some ways. The observation is nice and low dimensional, but we're using this very scalable method, diffusion policies or behavioral cloning, to actually learn from that data. And you can see there's a crossover point here. So once you get to about 30 demonstrations, the best performance is actually from behavioral cloning rather than this in-context learning. So if you've got lots and lots and lots of data for a task, behavioral cloning often does work quite well. But if you haven't got very much data, then something more structured, like using a pre-trained large language model to do your reasoning, can often work quite well. Okay, so I'm just going to finish off with a project that we published last year called Instant Policy. And the origins of this project were looking at that project that I just taught you about then, and thinking, well, that neural network, that large language model, even though it is able to do in-context learning, it wasn't trained to do. It wasn't trained to be good at understanding robotics data. So it's just a large language model. It's good at understanding text. It's not good at understanding robotics data, or at least it's not supposed to be good at it. Turns out it is, reasonable and it does a good job, and it was interesting to do that project. But we thought, well, maybe we can design our own model that does in-context learning, but that model is actually designed to work with robotics data. So this is going to look very different now to just prompting a large language model. It's going to be the same principle in that we want this instant learning, so we put at the input of a neural network the demonstrations plus the observation, and then we want the robot to instantly learn that task. But the structure of that neural network and the data it's trained on are going to look very different. So there are a couple of really important priors that we had to think about in order to design our own in-context learning neural network. The first is the fact that images and actions are not in the same space. So images are 2D or 3D images, but actions are these kind of sixed off trajectories through 3D space. So they're not the same space. Whereas beforehand with the large language model, the inputs and the outputs were just text. It was 3D positions of objects. So there was this sort of regularization there because you're inputting the same data that you're outputting, and so when the inputs and outputs are in the same domain, it's a little bit easier to learn that problem. Whereas here in robotics, you've got an image and then you've got a 3D or sixed off pose or trajectory, and that's something we need to map between. And naively doing this mapping is pretty hard. The other kind of prior is that in robotics we don't have very much data. So a little bit like how one of the previous projects I taught you about, we use simulation data to do that unseen object pose estimation. to train our in-context learning model, we're also going to use simulated data rather than collecting lots of real-world data. So here's how we address that first point, the fact that images and actions are not in the same space. So we're going to represent the environment state as a point cloud observation, and we're going to embed this in a graph neural network. So each of these points here, each of these green points represent points on the object. Each of these has some feature encoding the geometry, the local geometry. And then there's edges here which represent relationships between these nodes. And then we have these points on the gripper. And the blue points represent where the gripper is in the world. And now the actions can just be represented by the motions of these blue points. And so the observations are 3D points, and then the motions of the gripper are also 3D points. So a little bit like the previous project, both actions and observations are now in the same space. And then this is what the graph neural network looks like when you deploy it. You collect a demonstration, and a demonstration is a sequence of observations and actions, or a sequence of motions of the objects and the gripper. So you can see here the gripper is going down to there and then moving up to do something. All right? And this is actually picking up that roll of paper and moving it to on the top of the pole. Move down, grab, pick up. So you've got 3 time steps here. And then we'll do that with another demonstration, but this time the objects are in a slightly different initial pose. So we've got 2 demonstrations. This now goes into the neural network, and the nodes get updated based on the positions of the 3D the objects in 3D space. Then what we're going to do is we're going to condition the neural network not only on these demonstrations but also the current state. The current state is this here, also represented by a graph neural network, so representing where is the gripper relative to the objects. And then what we're going to do is predict these future actions. So predicting action 1, action 2, 3, 4, 5, action T is a future, a prediction of the future actions. And so if you can create a neural network like this, you could condition it on the demonstrations plus a live observation, and it would instantly predict what the values of these blue nodes are, which are the actions. So now we need to train this neural network on some data. And so we need data where there's a demonstration here, plus maybe another demonstration, and a current state, and some actions in the future. And what we found is, and this is, the prediction is done with a diffusion process here, so we're actually denoising actions, so it's graph diffusion process. So we start with noisy actions, and what the graph neural network does is it predicts how to denoise those noisy actions. And then the data that we trained this on was this simulated data, and we call these pseudo demonstrations. So these are kind of random objects with random poses relative to each other, but they're not real tasks. Like, we don't really care about like moving a bottle relative to a hat, or moving a piano next to a tap. These are not real objects. They're not real tasks that we care about. We just bringing in random objects and moving them relative to each other in random ways. But there is consistency within these demonstrations. So here, we're moving the piano to the same relative pose to the tap and then moving it down. Here, we are rotating the bike in the same way in each time. Here, we're moving the bottle to the same pose relative to the hat and then moving it in the same way. So each of these is an example of a semantically consistent demonstration. They're not real tasks, but there is consistency between each one. And so what we can do is then we can say, right, if this is one demonstration and this is another demonstration, then for an image of this scene, we want to predict these actions. So we need 3 demonstrations, one for that, and then one for this. And so we then collect random trajectories that are semantically consistent, but they don't need to be realistic tasks. Yeah, and so we have this sequence of, the context is basically a sequence of demonstrations. And we can have as many as we want. So this is a graph neural network. We can keep on adding demonstrations as and when necessary. We could have one demo, but we could also have two, we could have three or four. And each time you add in a demonstration, the robot will be able to condition on more than one demonstration. And this is what this looks like when we deploy it. So this is my student Vitalis in our lab. He's going to teach a robot how to pick up a bowl and place it on top of another bowl. And that's a single demonstration. And now he's going to step back, and this is one uncut video. And we're simply prompting that graph neural network with this one demonstration. And this is a closed loop policy. So you can see the object is moving around, and the robot's able to react to that movement. And a lot of that behavior, like, we didn't have to teach it with that one demonstration. That behavior is in the simulated data, which gives it this ability to react as you disturb the environment. Here's another example. We are showing how to close a box, and then we're going to put the box somewhere randomly. We're going to take that demonstration that we just showed, and we're going to use that to condition the neural network. And now the robot is able to just perform that task instantly, and it's a closed loop policy again. You can see it's taking in an image and reacting to the motion of the object. This is really interesting. So because this is a graph neural network, and it's a graph attention neural network, so we have this concept of attention that you also get in transformers. And we're visualizing the attention here. So we're visualizing how much attention is applied to these different states within the demonstration. So this is a demonstration, picking up a phone and placing it on the handset. And these videos are synchronized. So as the robot, this is what happens during testing, as the robot moves through the task and picks up the phone, it applies attention to the part of the demonstration that's just slightly ahead of where the robot is at that point in time. So it's kind of looking ahead and thinking, okay, where am I within this demonstration? And I should pay attention to that part of the demonstration and use that to figure out what the correct action is. Here's another a really nice thing you can do with this instant learning ability. So we're showing the robot how to open this big box. One demonstration, we're going to test the robot on this box. And we see that it's able to open the lid of the box because we taught it on that box, and it's able to learn the task instantly as before. Now we're going to test it on this smaller box. This time the robot actually fails the task. It sort of has an idea as to what it should be doing, but it's not able to do it perfectly. But we can come in instantly and correct that. We can provide a new demonstration on this task. And now the model is being conditioned on two demonstrations, the one on the big box and the one on the small box. And it's able to learn both those tasks. And now what we can do is we can start putting in other objects. So here's a medium-sized box, and the robot's never even seen a demonstration of this box. And again with this box, it's a medium-sized box. It's sort of in between the big one and the small one. It's never seen this box before, but because we're now conditioning the model on demonstration of the big box and a demonstration of the small box, it's able to generalize and start working with these medium-sized boxes. And finally, because the actions are represented just by motions of the gripper, if we have a hand tracking model, we can pretend that the human is a robot, and we can actually command the robot using human hand demonstrations. So here we're moving the hand to pick up the cup, and we're using a hand tracker to track the motion of the hand and kind of pretending that is a robot gripper. And then we can just deploy the robot on that same task. So now we don't even need to teach the robot on the robot's own hardware. We can teach the robot using human hand demonstrations. Sorry, I skipped ahead a bit there. So let's just watch that again. Moving our hand down, there's a hand tracker algorithm going on, and that gives you the poses of the hand. And then we just condition the neural network on the poses of that hand as before, and we've taught the robot instantly how to perform this task. And so not only is this robot able to learn this task from one demonstration and then no further waiting around, we're actually able to do this without even needing to sort of bend over and move the robot itself. We can just use our own hands. There are limitations to this because there's going to be some error in the estimation of the human's hand, whereas if you do the demonstration directly on the robot, it's going to be more, the actions are going to be more accurate. But this is significantly more convenient. So there's a bit of a trade-off here. So for some tasks where maybe you don't need a huge amount of accuracy in the actions, just providing those demonstrations with a human hand demonstration is sufficient. Okay, and that's all I wanted to talk about really. So I'd just like to thank my team who've worked on all of this with me, and I'm happy to take any questions.